Hello, Mark. I'm Candace. My score number is 30. I'm sophomore at NCUE. I'm going to read Hugh, Her, the new bonnets that others run, climb, and dance. Looking deeply inside nature, through the magnified glass of science, designers extract principles, processes, and materials that are forming the very basis of design methodology. From synthetic constructs that resemble biological materials to computational methods that emulate neural processes, nature is driving design. Design is also driving nature. In realms of genetics, regenerative medicines, and synthetic biology, designers are growing novel technologies not foreseen or anticipated by nature. Bonnets explore the interplay between biology and design. As you can see, my legs are bionic. Today, I will tell human story of bionic integration, how electromechanics attached to the body and implanted inside the body are beginning to bridge the gap between disability and ability, between human limitation and human potential. Bionics has defined my physicality. In 1982, both my legs were amputated due to tissue damage from frostbite incurred during a mountain climbing accident. At that time, I didn't view my body as broken. I reasoned that a human being can never be broken. Technology is broken. Technology is inadequate. This simple but powerful idea was a call to arms, to advance technology for the elimination of my own disability, and ultimately the disability of others. I began by developing specialized limbs that allowed me to return to the vertical road of rock and ice climbing. I quickly realized that the artificial part of my body is mobile, able to take on any form, any function, a blank slate for which to create, perhaps, structures that could extend beyond biological capability. I made my height adjustable. I could be as short as 5 feet or as tall as I liked. Laughter. So when I was feeling bad about myself, insecure, I would jack my height up. Laughter. But when I was feeling confident and swot, I would knock my height down a notch just to give the competition a chance. Laughter, applause. Narrow edge feet allow me to climb steep rock fissures where the human foot cannot penetrate, and spike feet enable me to climb vertical iceworks without ever experience muscle-like fatigue. Through technological innovation, I returned to my sport stronger and better. Technology had eliminated my disability and allowed me a new climbing prowess. As a young man, I imagined a future world where technology so advanced could rid the world of disability, a world in which neural implants will allow the virtual empire to see, a world in which the parrots could work without body exoskeletons. Sadly, because of deficiencies in technology, disabilities is rampant in the world. This gentleman is missing 3 limbs. As a testimony to current technology, he's out of the wheelchair. But we need to do a better job in bionics to allow one day full rehabilitation for a person with this level of injury. At the MIT Media Lab, we've established the Center for Extreme Bionics. The mission of the center is to put forth fundamental science and technological capability that will allow the biomechatronic and regenerative repair of humans across a broad range of brain and body disabilities. Today, I'm going to tell you how my legs function, how they work. As a case in point for this center, Now I made sure to shave my legs last night because I knew I was showing them off. Laughter. Bionics entails the engineering of extreme interfaces. The three extreme interfaces my bionic limbs: mechanical, how my limbs are attached to my biological body; dynamics, how they move like flesh and bone; and electrical, how they communicate with my nervous system. I'll begin with mechanic interface. In the area of design, we still do not understand how to attach devices to the body mechanically. It's extraordinary to me that in this day and age, one of the most mature, oldest technology in a human timeline, the shoe still gives us blisters. How can that be? We have no idea how to attach things to our bodies. This is the beautifully liberal designs work of Professor Nira Oxman at the MIT Media Lab, showing spatial exoskeletal impedances, shown here by color variation in this 3D printed model. Image: a feature where clothing is stiff and soft where you knit it. Where you knit it for optimal support and flexibility without ever causing discomfort. My bionic limbs are attached to my biological body via synthetic skins with stiffness variations that mirror my underlying tissues biomechanics. To achieve that mirroring, we first developed a mathematical model of my biological limb. To that end, we use image tools such as MRI to look inside my body to figure out the geometries and locations of various tissues. We also took robotic tools. Here's a 14 actuator circle that goes around the biological limb. The actuators come in, find the surface of the limb, measures its unloaded shape, and then they pushed on the tissues to measure tissues components at each anatomical point. We combine this imaging and aerobic data to build mathematical descriptions of my biological limb, shown on the left. We see a bunch of points or nodes. At each node, there's a color that represents tissue's components. We then do a mathematical transformation to the design of the synthetic skin shown on the right, and we've discovered optimality is where the body is stiff, the synthetic skin should be soft. Where the body is soft, the synthetic skin is stiff. And this mirroring occurs across all tissue complexes. With this framework, we've produced bionic limbs that are the most comfortable limbs I've ever worn. Clearly, in the future, our clothing, our shoes, our braces, our prostheses will no longer be designed and manufactured using Erickson's strategies, but rather data-driven quantitative frameworks. In that future, our shoes will no longer give us blisters. We're also embedding sensors and smart materials into the synthetic skins. This is a material developed by SRI International California under electrostatics effect. It changes stiffness. So on a zero voltage, the material is compliant. It's flowy like paper. Then the buttons pushed, a voltage is applied, and it becomes stiff as a board. Tapping sounds. We embed this material in the synthetic skin that attach my bionic limb to my biological body. When I walk here, it's no voltage. My interface is soft and compliant. The buttons pushed, voltage is applied, and it stiffens, offering me a greater maneuverability over the bionic limb. We're also building exoskeletons. This exoskeleton becomes stiff and soft in just the right areas of the running circle to protect the barnacle joints from high impacts and degradation. In the future, we will be wearing exoskeletons in common activities such as running. Next, dynamics interface. How do my bionic limbs move like flesh and bone? At my MIT lab, we study how humans with normal physiological stand, walk, and run. What are the muscles doing, and how are they controlled by the spinal cord? This basic science motivates what we build. We're building bionic ankles, knees, and hips. We're building body parts from the ground up. The bionic limbs that I'm wearing are called biomes. We've been fitted to nearly 1,000 patients, 400 of which have been wounded U.S. soldiers. How does it work? At Hugh strikes under computer control, the system controls stiffness to attenuate the shock of the limb hitting the ground. Then at mid-stance, the bionic limb outputs high torques and powers to lift the person into the walking stride. Comparable to how muscles work in the calf region, this bionic propulsion is very important clinically to patients. So on the left, we see the bionic device worn by a lady. On the right, the passive device worn by the same lady that fails to emulate normal muscle function, enable her to do something everyone should be able to do, go up and down their steps at home. Bionics also allows for extraordinary athletic feats. Here's a gentleman rounding up a rocky pathway. He's Steve Martin, not the comedian who lost his fist in a bomb blast in Afghanistan. We're also building exoskeletal structures using these same principles that wrap around the biological limb. This gentleman does not have any leg conditions, any disability. He has a normal physiological, so these extra skeletons are applying muscle-like torques and powers, so that his own muscle need not apply those torques and powers. This is the first exoskeleton in history that actually augments human walking. It significantly reduces metabolic cost. It's so profound in its augmentation that when a normal healthy person wears the device for 40 minutes and then takes it off, their own biological legs feel ridiculously heavy and awkward. We're beginning the age in which mechanics attached to our body will make us stronger and faster and more efficient. Moving on to electronic interface. How bionic limbs communicate with my nerve system. Across my residual limbs are extrodes that measures the electrical pulse of my muscles. That's communicated to the bionic limb. So when I think about moving my phantom limb, the robot tracks those movement desired. This diagram shows fundamentally how the bionic limb is controlled. So we modeled the missing biological limb, and we've discovered that reflexes occurs, how the reflexes of spinal cord are controlling the muscles. And that capability is embedded in the crypts of the bionic limb. What we've done then is we modulate the sensitivity of the reflex, the motospinal reflex with the neural signal. So when I relax my muscles in my residual limb, I get very little torque and power. But the more I fire my muscles, the more torque I get, and I can even run. And that was the first demonstration of a running gait under neural command. Feels good. Applause. We want to go a step further. We want to actually close the loop between the human and the bionic external limb. We're doing experiments where we're growing nerves, transected nerves to channels or microchannel areas. On the other side of the channel, the nerve then attaches to cells, skin cells, and muscle scales. In the motor channels, we can sense how the person wishes to move. That can be sent out wirelessly to the bionic limb. Then sensory information on the bionic limb can be converted to stimulations in ejection channels, sensory channels. So when this is fully developed and for human use, persons like myself will not only have synthetic limbs that move like flesh and bone, but actually feel like flesh and bone. This video shows Visa melted shortly after being fitted with 2 bionic limbs. Indeed, bionics is making a profound difference in people's lives. Video, Lisa melted. Oh my god. LM. Oh my god, I can believe it. Video, laughter. LM. It's just like I've got a real leg. Woman, now don't start running. Man, now turn around and do the same thing walking up, but get on your heel to toe like you would normally just work on level ground. Try to walk right up the hill. LM. Oh my god. Man, is it pushing you up? LM. Yes, I'm not even. I can't even describe it. Man, it's pushing you right up. You've heard. Next week, I'm visiting the center. Thank you, thank you. Applause, thank you. Next week, I'm visiting the Center for Medicare and Medicaid Services, and I'm going to try to convince CMS to grant appropriate code language and pricing, so this technology can be made available to the patients that need it. Applause. Thank you. Applause. It's not well appreciated, but over half of the world's population suffers from some form of cognitive, emotional, sensory, or motor conditions, and because of poor technology, too often, conditions result in disability and a poor quality of life. Basic level of physiological function should be a part of our human rights. Every person should have the right to live life without disability if they so choose. The right to live life without severe depression, the right to see your loved one in the case of seeing impaired, or the right to walk or to dance in the case of limb paralysis or limb amputation. As a society, we can achieve these human rights if we accept the propositions that humans are not disabled. A person can never be broken. Our built environment, our technology, and broken and disabled. We, the people, need not accept our limitation, but can transcend disability through technological innovation. Indeed, through fundamental advance in bionics in this century, we will set the technological foundations for an enhanced human experience, and we will end the disability. I'd like to finish up with one more story, a beautiful story, the story of Andrea Hassel Davis. Andrea lost her legs in Boston terrorist attack. I met Andrea when this photo was taken at Spalding Rehabilitation Hospital. Andrea is a dancer, a boring dancer. Andrea breathes and lives dance. It is her expression. It is her art form. Naturally, when she lost her limb in Boston terrorist attack, she wanted to return to the dance floor. After meeting her and driving home in my car, I thought, I'm an MIT professor. I have resources. Let's build her a bionic limb to enable her to go back to her life of dance. I brought in MIT scientists with expertise in prosthetics, robotics, machine learning, and biomechanics, and over 200-day research period, we studied dance. We brought in dancers with biological limbs and we studied how they move, what forces they applied on the dance floor, and we took those data and we've put forth fundamental principle of dance, flexive dance capability, and we embedded that intelligence into the bionic limb. Bionic is not only about making people stronger and faster. Our expression, our humanity can be embedded into electromechanics. It was 3.5 seconds between the bomb blast and the Boston terrorist attacks. In 3.5 seconds, the criminals in the cars took Andren off the dance floor. In 200 days, we pushed her back. We would not be intimidated, brought down, diminished, conquered, or stopped by acts of violence. Applause. Ladies and gentlemen, please allow me to introduce Andrea Held Davis. Her first performance since the attack. She's dancing with Christian Leitner. Applause. Music. Ring My Bell, performed by Eric Alexa. Applause. Ladies and gentlemen, members of the research Elector Rost and Ethan Villagraci Karski. Electrode and Nathan. Applause. Thank you. Thank you, Mark.